Today we're going to be talking about action potential, and an action potential is simply the transmission of an electrical signal down the cell membrane of a neuron. So let's go ahead and draw a neuron to get oriented, and I'm going to go draw a neuron just like this. I'm going to draw a triangle. This is going to represent the cell body of the neuron. There's the nucleus. I'm going to put some dendrites on here and some axon terminals. All right. So the electrical signal is always going to move this way in a neuron. It's going to start at the dendrites, move down the cell body, the axon, to the axon terminals, and then we're going to jump across the synaptic cleft, which we'll talk about in another video. This entire neuron is covered with a cell membrane. And the cell membrane is where the action potential is going to take place. So let's go ahead and take a little section of the cell membrane here. I'm going to choose to take it from the axon, but I could have taken it from the dendrites, the cell body, the axon terminals, or anywhere else. So here we go. We're going to take that little stretch of cell membrane and we're going to enlarge it and take a look at it. So here we go. This is going to represent our cell membrane. So let's go ahead and we'll label that. That's the cell membrane. And we're going to go ahead and draw in some transport proteins. So here's one transport protein. And this is going to be called a voltage-gated sodium transport protein. I'll put TP. The next transport protein is going to be a potassium transport protein. So that's going to be a voltage-gated potassium transport protein. And voltage-gated simply means that that transport protein opens up in response to a change in voltage, which we'll talk about in just a minute. Now the last transport protein is going to be a sodium-potassium pump. Now let's get oriented here. This is going to be the outside of the neuron. We could call this the extracellular fluid. And this will be the inside of the neuron, or the cytoplasm. All right, so there we go. Now, the sodium-potassium pump is going to be very important. It's actually going to put ions in a particular place. So the sodium-potassium pump is going to pump, and whenever we use the word pump, we're talking about active transport. We're talking about the need for ATP. So the sodium-potassium pump is going to pump sodium ions outside of the cell membrane. So let's go ahead and say that we have lots of sodium ions outside. Lots of sodium ions. And at the same time, the sodium-potassium pump is going to pump all the potassium ions inside. So the inside is going to have lots of potassium ions. In addition to that, the inside is going to have, and I guess I can do this with orange, it's going to have lots of proteins. There's lots of proteins on the inside of the cell. And these proteins tend to be negatively charged. There's lots of atoms on these proteins that have negative charges. In fact, there's so many negative charges on these proteins that overall the inside is going to be negative. So this is going to predominate. Even though we've got lots of positive potassium ions, there's so many negatively charged proteins that this wins out. And overall, the inside of the cell is going to have a negative charge. And the outside is going to be overall positive. Now we can measure this. If we take a voltmeter, which measures voltage, just like you could measure the voltage of a battery. If you look at a AAA battery or a AA battery, you'll see that it says 1.5 volts. That's a measure of the charge. Batteries have a separation of charge. You have a positive end, you have a negative end. And when you hook up a battery, electrons come out of the negative end and go to the positive end. Something similar to that is going to happen here, in the sense that we're going to have a separation of charge. And having that separation of charge allows us to do work. And in this case, the work is going to be the transmission of an electrical signal, meaning an action potential. So I'm going to go ahead and draw a voltmeter here. So this is going to be my voltmeter. And on this voltmeter, I'm going to put a little dial. There it is right there. And out of the voltmeter is going to come one lead that we're going to put into the extracellular fluid. So this one lead is going to go outside the cell membrane. And the other lead is going to go inside the cell, into the cytoplasm. And we have small little leads and needles that can actually do this. We can measure the voltage of a cell membrane, just like we can measure the voltage of a battery. Now, when we actually measure the voltage here, when there's no action potential coming through here, all right? So when this cell membrane is at rest, when really there's no activity taking place, we're going to get a number of negative 70 millivolts. That's pretty small. Milli means thousandths, so that's 70 thousandths of a volt, a very, very, very small number. And the negative here refers to the fact that overall the inside of the cell membrane is negatively charged. It does not mean that this number is less than 0. That's just not so. It means that overall the inside of the cell membrane is negatively charged. Now, this number, negative 70 millivolts, occurs when our membrane is polarized, meaning we have a nice separation of charge here. So we're going to say that the membrane is polarized. And because the cell membrane is at rest here, this is referred to as the resting membrane potential. Or we could call it the voltage. All right. All right. Now, when a signal gets near this section of the membrane, and everybody has probably had an experience with a balloon where you take a balloon and you rub it on your head and then you feel all that static charge. In fact, as you bring that balloon closer to you, you can feel the tingling get stronger and stronger. That's the static electricity getting closer and closer to you. You can sense that. Well, it turns out that these voltage-gated transport proteins can also sense a charge getting closer and closer to them. So as this action potential is moving down the cell membrane, that charge is getting closer and closer. And these guys can feel it. They can feel that charge getting stronger, that change in voltage getting stronger and stronger, until finally we reach what we call the threshold potential. That voltage that is strong enough to make these guys respond. And the way they respond is by opening up. Now it turns out they don't both open at the same time. This guy, the voltage-gated sodium transport protein, responds very quickly. Right away. As soon as he senses it, bang, opens up. The potassium transport protein is going to also sense that and begin to open up. He begins to open up very slowly. Kind of like a turtle here. Opens up very slowly. So this guy opens up first. And when this guy opens up, he's a sodium transport protein. So he's going to allow sodium to pass through him, and only sodium. So there's lots of sodium out here, very little in here. Sodium's going to move down its concentration gradient, so sodium's going to go into the cell. Lots of sodium's going to pour into the cell. And this is going to happen for a few milliseconds until this guy automatically closes. Now as sodium pours into the cell, this negative 70 millivolts is going to start to change. Now we got positive charge coming in, so that's going to make the inside less negative. So this negative 70 is going to start going upwards. It's going to negative 69, negative 68, negative 67. In fact, it's going to keep going until we get to about positive 60 millivolts. That's how far it's going to go. And we say that the membrane now is depolarized. It's depolarized. That means that there's no longer a separation of charge. And that is a signal right here. Our membrane potential, our voltage has changed. And that change in voltage is the signal. Now, this guy is closed, and this guy has finally gotten around to open up. Now, what's going to happen here is there's lots of potassium in here, very little out here. So again, potassium is going to move down its concentration gradient and outside of the cell. Now we've got a bunch of positive charge leaving the inside. So this number is going to start to become less and less positive. So it's going to start going down, 59, 58, 57. In fact, we're going to go all the way down to about negative 80 millivolts. We're actually going to overshoot where we were before. So we're at negative 80 millivolts. And we say that the cell membrane here is repolarized. It's repolarized. It means our numbers are back to where they should be. The charge is back to where it should be. Almost. Almost. A little bit different, but almost. But we got a problem here. We can't send another signal through here. And the problem is, even though our numbers are looking pretty good, pretty close to what they should be, the ions are in the wrong place. So that's where the sodium-potassium pump comes in. Once the sodium-potassium pump realizes that the ions are in the wrong place, it's going to start pumping these ions back. And that takes energy. That takes energy in the form of ATP. All right, so this guy's going to kick in. The sodium is going to get pumped back to where it belongs. And the potassium is going to get pumped back to where it belongs. And that's going to happen very quickly, in a matter of milliseconds. And this is going to bring our number back to negative 70 millivolts. And again, we're back to the resting membrane potential. All right? So I'll put resting membrane potential, I'll abbreviate that. And our membrane, again, is polarized. It's ready to transmit another electrical signal, another electrical impulse. And that is an action potential. So again, an action potential is just the transmission of an electrical signal down the cell membrane. And this electrical signal is simply a change in voltage. It's almost like dominoes. Now, here's a section of the cell membrane. The next section of the cell membrane is going to look exactly the same. So as soon as the voltage begins to change here, the next set of transport proteins is also going to sense this, and they're going to begin to respond and open up. And the voltage is going to change there. And then the next set of proteins, down a little bit further on the cell membrane, is also going to sense that, and they're going to begin to open up. So it's like a domino effect all the way down to the axon terminals. And that's what an action potential is.